In this video, we are going to discuss about the negation of quantified statements. If you recall, quantified statements also have truth values of either true or false. And we are also interested in sometimes considering the negation of these quantified statements. And the rules for negations for quantifiers are called De Morgan's laws for quantifiers. Recall that we have the universal and the existential quantifiers. And the universal quantifiers denoted by this expression is false when there is just one x or at least one x where the p of x is false. Meanwhile, the existential quantifier is false if p of x is false for all x. So let us start with the universal quantification. So for all x p of x in the domain D, if we can list down each of the elements of D, then we can express this universal quantification using the statement p of x sub 1 and p of x sub 2 until p of x sub n. Note that the universal quantification is tied to conjunction, and this will only be false if we can at least find one x wherein the p of x will be false. So for example, if we have 10 elements in the domain, if there is just one x that will make this p of x false, then the universal quantification is false. So taking the negation of the universal quantification, it is equivalent to just taking or applying the De Morgan's law. Okay, so applying the De Morgan's law to this whole expression, we distribute the negate each of the elements, and the connectives also become 4. So consider also this statement: there exists x in D such that not p of x. So because the existential quantifiers is tied to this junction, we can express it using this statement: the not of p of x sub 1 or the not of p of x sub 2 or the not of p of x sub n. So we can see that the negation of the universal quantifier or the negation of for all is logically equivalent to the existential na quantifier. There exists x in D such that not p of x, or equivalent to there is at least one that is not. Okay, again, the negation of for all is logically equivalent to there is at least one that is not. Meanwhile, for the existential quantifier, if we can list down each of the elements in the domain, then it is equivalent to p of x sub 1 or p of x sub 2 until p of x sub n. Note that the existential quantifier is tied to this junction. Now, if we take the negation of this existential quantifier, then we are also simply applying De Morgan's to this whole expression. Okay, and so we are going to negate each of the predicates, and we take the connective instead of r. Okay, and meanwhile, consider this universal quantification for all x in D, not p of x. Because this is tied to conjunction, this is equivalent to this statement: the not of p x sub 1, p of x sub 1, not of p of x sub 2 until not of p of x sub n. So as you can see, they are logically equivalent. So this existential quantifier, as we have mentioned, refer to some r. Okay, so its negation then is equivalent to all are not. Okay, so some negation of some r is equivalent to all are not. Note that again, this existential quantifier is false when p of x is false for all of the x. Okay, so here's just a summary. Let us find the negation of the statement all mathematicians wear glasses. Suppose the domain is the set of all mathematicians, and we have a predicate p of x such that x wears glasses. So we can rewrite the statement as for all x in D, P of x. So the negation of the universal quantification is there exists x in D such that not P of x. In other words, there is at least one that is not. Okay, so expressing the negation of this statement, we have there exists a mathematician who does not wear glasses, or there are some mathematicians that do not wear glasses. Okay, and then we have another example. So the statement is some politicians are honest. So the domain is the set of all politicians, and we have a predicate P of x such that x is honest. We can rewrite the statement as there exists x in D such that P of x. So recall that the negation of an existential quantifier is for all x in D, not P of x. In other words, if the existential quantifier refers to some R, the negation is all R not. So the negation of a statement will then be all politicians are not honest, or no politician is honest. Now, another example, all Canadians eat sushi. So the domain will be the set of all Canadians, and the P of x will be such that x eats sushi. And we can rewrite this into for all x in D such that P of x. So the negation of the universal quantification is there exists x in D and not P of x. In other words, there is at least one that is not. Okay, so the negation is some Canadians do not eat sushi, or there are some Canadians that do not eat sushi. Okay, let's have some more example. We have the statement for all x such that x squared is greater than x. So what will be the negation of this statement? So we take the negation we apply negation to the universal quantifier. So this will be equivalent to there exists x such that not of x squared is greater than x. So note that we are simply negating the property of this, or the property of x. Okay, so the negation of x squared is greater than x will be x squared is less than or equal to x. Now, what is the negation of there exists x such that x squared is equal to 2? So taking the negation of this existential statement, it is equivalent to for all x, not of x squared equals 2. So taking the negation of this property, so we have x squared is not equal to 2. Now let's proceed to a universal conditional statement states that for all x in D, the P of x implies Q of x. So taking the negation of this will be equivalent to there exists x in D, and then we take the negation of the predicate. So we have the not of P of x implies Q of x. But we know that the negation of an if P then Q statement is logically equivalent to P and not Q. Hence, we can replace this with P of x and not Q of x. For all real number x, if x is greater than 10, then x squared is greater than 100. So we can see here an if-then clause, meaning we have a conditional statement. So we can express this as P of x implies Q of x, wherein P of x is greater than 10, and Q of x is x squared is greater than 100. So then the implication will then be if x is greater than 10, then x squared is greater than 100. So we wanted to take the implication of or the negation of this statement for all real number x. If x is greater than 10, then x squared is greater than 100. So we know that the negation of a universal quantifier is expressed this way. We have there exists x in D such that P of x is greater than not Q of x. So we have already proven this in the previous slide. So this statement's negation will then be there exists a real number x. So we retain P of x. So x is greater than 10 and the negation of Q of x. So we have the x squared is less than or equal to 100. Now I have another example. If a computer program has more than 100,000 lines, then it contains a bomb. Negation is that, note that the negation of all R, so as you can see, we have all computer programs is, there is at least one that is not. So its negation will be, there is at least one computer program that has more than 100,000 lines and does not contain a bug.